Hello, Mighty Six. We are looking at a test on Tuesday, trying to get it out of the way before we get busy with the arts festival. So let's go ahead and at least tonight or today, whenever you're looking at this weekend, let's at least look at the topics that you'll need to be familiar with. Then in Monday's class, we'll actually do some of these problems and review and be a good practice exercise, and we'll be set for Tuesday. So the first topic since the last test, it's all on functions, so keep that in mind. We're going to look at evaluating functions. So if you would recall that y equals x cubed minus 2x plus 3. If I ask you to evaluate it, you will switch to the functional notation, which just replaces the y with the equivalent f of x. X cubed minus 2x plus 3. And then I'll ask you to do something like find f of 2. So when you find f of 2, that means this functional notation tells you wherever there's an x, it comes out like this, so we're going to put in a 2 for x. So we get 2 cubed minus 2 times 2 plus 3, and that is 8 minus 4 plus 3, or 7. Okay, easy peasy. But then we kicked it up a bit to see that there are functions that are described in pieces. And intelligently, we call those piecewise functions. So this one could tell us the function does this when x is greater than or equal to 5, and it does this when x is less than 5. So I want you to find f of 10. So you have to know which piece you are dealing with. Well, 10, is it going to be in the greater than 5 or less than 5 category? Obviously, greater than, so you're going to use this piece. So you're going to put the 10 into the 3x, and you're going to get 30 out. So f of 10 equals 3 times 10. All right, because we're following this piece. If we had f of 4, then we would be in this piece for the x. These are the x values. It's less than 5, so we're going to use this piece. We put 4 into this function. We get 2 times 4 plus 1, or 9. All right, easy peasy. All right, what do you think about that, Adam? All right, show me strong in math. I want you to get all of the evaluate problems right. Not just Adam, all of you. All right, then we kicked it up even further and we learned the difference quotient. Now I'm not as quick to call this easy peasy because you seem to be deer in headlights at the board when I ask you to do these. So they should be similar in this. It's similar to this evaluating functions in that here is the difference quotient. There are a couple different difference quotients. Sorry, you get seasick. The difference quotient I'm going to ask you to do is more like the one we'll see in calculus. There are other forms of a difference quotient that work as well, but I'm going to use f of x plus h minus f of x divided by h divided by h. This is the difference quotient. All right, so you see how far I will humble myself to get you to learn this stuff. So go figure. Let's look at the difference quotient. You must know this by heart. So sing away until it is in your psyche. F of x plus h minus f of x divided by h. And again, I can't really convince you of its value until you see it in the calculus, so you'll just have to put that part on hold. But during pre-calculus, you have to find the difference quotient for given a function. So I'm going to give you y equals x squared plus 2x minus 1 and ask you to find the difference quotient. So if you understand how to follow this, go ahead and do it in your comp book. Stop the video and try it, and then we will confirm your results. So again, here's the difference quotient, and where'd my light go? That's kind of dim. I can't go light on this one. All right. Sorry, technical difficulties, lighting. Alright, I'm just going to go with it. Sorry about that. But we have f of x equals x squared plus 2x minus 1. That's what that says if it's not glared out. Here's the difference quotient. Now, why does that show up so nice? I don't know. Alright, so there's the difference quotient, and I want you to apply this function, find the difference quotient for this function. So, this tells me what f of x is, but the difference quotient starts with asking what's f of x plus h. So that's an evaluate step, except instead of putting in a 3 or a 2, we're putting in an x plus h. So this says find the function putting in f of x, putting in x plus h. So over here, wherever there's an x, I'm going to replace it with an x plus h. So that is right there. So up to there. So I put in, everywhere there was an x, I put in an x plus h. So do you follow that? And there's my minus 1. So it stops right there. Alright, so that is this part. So I've accomplished that by putting an x plus h everywhere the function had an x. Then I hit this minus sign. So we are just going to be mathematical puppy dogs. I'm going to say do it and you do it because, again, the understanding why this is so powerful and important will be next year. So minus f of x, so that function has been defined as this. Notice the minus sign in front of this whole function will affect everything behind it. So I go ahead and change the signs right away, or I collect them in a set of parentheses so I can get it later. And that's just divided by h. So h is unchanged. That h is just h. It's not put into the function. It does not say f of h. It just says h. H is h. Everyone walking down the hall knows that. Alright, so here I expand it. What is x plus h squared? You should have come to me knowing that when you square a binomial, you square that, you just multiply these together and double it. So that's the quick version. If you don't believe me, you always do. I go x plus h times x plus h. That's what that means. So you'll have 4 steps and you'll combine like terms and you will get this values. Then we get plus 2 is distributed to the x and the h, and then the minus 1, and then this bigger minus that goes to everything behind it, changing the signs as so, divided by h. Alright, then it becomes a lot of fun because all these things cross out. So the x squares cross out, the 2x and the minus 2x, the minus 1 and the plus 1. So you know you're on the right track if a lot of things drop out. And notice the terms that remain all have h in them, which causes us to simplify further. So this h will cancel an h in each term. And if there is a term without an h, I cannot do that. So h, one of these, and this one. So if the h is in every term, I can simplify further. And the h in the denominator is canceled, and we get 2x plus h plus 2. Alright, this is an amazing result for next year, not so much for this year. Alright, so be a math monkey and just do it, and the understanding will be in your math future. Alright, here we have the 8 parent functions. I left one out, and that's because I can't think of it. So your job is to come up with one of the 8 that I forgot, if it comes to me. So I have y equals a constant, like 3, y equals x squared, y equals x cubed, y equals the square root of x, y equals the absolute value of x, and can't remember, and y equals the greatest integer function. Alright, I know there's an obvious one that I forgot. So there are 8 parent functions. So if you would fill in this one, I would appreciate it. You will have to, on command, as math puppies, if I command you to give me one of the functions, you must know its graph. you must know the domain, range, x and y intercepts, increasing, decreasing, or constant, even, odd, neither, even, odd, or neither, and the symmetry. And symmetry can be x, y, or symmetric to the origin. For example, if I say y equals square root of, y equals absolute value of x, you have to give me that graph. And you have to give me the domain. So domain is what is the x values doing. So we say x equals, the domain is x is an element of the real such that, and then we write down the possible values for x. However, since this goes forever in both directions, what values of x are actually involved with this graph? If I go up or down, will I meet this graph for all values of x? I will. So to communicate that, we don't need our such that line. We can just close the brace, and everyone knows that the domain x is an element of reals tells you that all real numbers are in the domain. Then we go to the range. It's not so for the range. And range, we're switching to what y values are connecting to this graph. So like this graph, if I go say y equals -2, if I go right and left, I will never intercept this graph. So what y values are involved with this graph? Well, as I go down, I'm never going to find any, but as I go up, the first one is 0. So y is an element of the real such that y is greater than or equal to 0, and you can see any value above will be in the range. All right, what are the x and y intercepts for this graph? Well, here's the y-axis, the x, they both intercept right there, so they're both the same in this graph, 0, 0. Decreasing, where is it decreasing, increasing, or constant? In this graph, constant means a portion of the graph is horizontal, so there's none like that. So we're going to do this from left to right, and like you're reading a book. So we'll put our little cart or our skier on the left and have it travel to the right. Notice it's going down originally, so we're going to say decreasing. We indicate that with interval notation. So it's going to come from, and we're going to talk about it in terms of the x values. So it's going to be decreasing from -infinity, and it's going to continue until right there at 0. So that's the decreasing part, and this is the way we communicate that to our fellow mathematicians. So then it's increasing, starting here, the card will be going up from 0 to +infinity. And this interval notation, it will communicate that. All right, and there's no sections where it's constant. All right, moving right along. Are you okay with that? Trent, what do you think? All right, even, odd, or neither comes up next. So we learned, this one's getting jumbled up, so I'll give a new, fresh graph. Right here is the absolute value graph again. And supposed to meet right at the origin. So make yours sketch better than mine. And we're looking at whether it's an even function, odd, or neither. So we decided if we go out x on one side and -x on the other side and find the values of the function, if they're equal, then we say it's even. If they're equal except for their sign, then we say it's odd, and if it doesn't follow either of those patterns, we say it's neither. So if we go out x, we say x is this amount, and -x would take us this way. So if I go up to evaluate the function, I find out where x hits the function, I read the value over here, so I call that f of x, or the y value. And if I go out -x and I go up and hit the function, I find I get to the same spot. So that's what happens when we have an even function. All right. symmetry, there are three choices: x, y, and symmetric to the origin. And it all depends if you fold it along these lines, and you'll get the same values. So if we fold along the x-axis, we'll see that this imprints down here, and there's no such function down here. But if we fold it along the y, this will imprint on this, and there's a perfect match. So we say it's symmetric to the y. All right, it has y symmetry. All right, what do you think about that, Drew? All right. Did I leave out something? No. I just want to make note. John, you shocked and amazed me one day when you told me, is an even function always symmetric to the y-axis? And the answer was yes. So I still am amazed that you noticed that. All right. So always share your insights, class, so you can further shock and amaze me. All right. Then you have to know how to take the basic parent functions and move them all around. So we'll stick with the absolute value function, which looks like that. And this number, if I put it out here, tells me it goes in a certain direction. Do you recall? Up 3. That's an up 3. What about this one? All right, I'm looking into your thought cloud, Dimitri. What's that plus 3 do to it? The plus 3 causes it to move it to the left or the right, unlike what you might think. So a plus 3 is a left 3 when the change is inside of the function, which I sometimes call hugging the function. Notice it's inside the absolute values. So that's a left-right. A negative sign out in front of the whole function is a reflection or a flip across the x-axis. Now if that negative hugs the variable inside the function, it flips across y. And we'll get to practice some of these on Monday. Alright, a value outside of the whole function when it's multiplied. Notice up here we were adding. So this is a multiply. We learned that this was a vertical stretch. So imagine what had this on a flexible piece of paper. We're going to stretch it vertically. So if this graph starts out like this and we stretch the paper vertically, do you see it would cause this to come closer in to the y-axis? It would close in on it. And the other way, when this is a number like a fraction between 0 and 1, this is when it's non-fractional. It can be fractional, but it's got to be greater than 1. So it could be like a 4/3, and that would also cause a vertical stretch. But a 1/3, if it's between 0 and 1, we have a vertical shrink. So that would make the original graph get fatter and closer to the x-axis. Alright, so the other two cases are going to be when the value, the change, the multiplier, the factor, is inside of the function. So there we have horizontal changes. So when the number was outside, it was vertical. Now we're inside, horizontal. So it's opposite. You recall when the number was outside, it was a vertical stretch. So this will be a horizontal shrink. So this time it's on a stretchy sock, and we're going to shrink it horizontally. So if the graph is sitting there like this, and you shrink it horizontally like this, push it together, it's going to go like that. And here it's going to be a horizontal stretch. So if I'm like this and I pull it apart like that, the function is going to widen. Alright, so we'll practice some of those. These is a quick review of what to expect on the test and the main concepts. And then we advance to graphing rational functions. And remember, rational means ratio or fraction. So we are expecting numerators and denominators. And we learned that if the numerator is less than the denominator, we graph it one way. When it's equal, we have a set of other principles. And lastly, the third is when the degree of the numerator is greater than the degree of the denominator. So, alright, let's start with the first case we learned, when the numerator's degree here is 1, degree here is 2, so this one fits. And we want to go va-ha, ha. Alright. So, let's see, Jordan, I haven't picked on you, so have in your mind for me so I can grab it. What is the va on this one? Well, as Jordan and everyone walking down the hall knows, we have to factor. So we have, who was it? Adam didn't, this doesn't seem to always stick. So put it in a place in your brain where it sticks. When you have a difference of two things that are squared, like x squared minus 4, it factors a plus b, a minus b. So a minus b, it doesn't matter which one you put first. So now you can, back to you Jordan, you can see clearly, you always look in the denominator, because wherever the denominator zeroes out, we have to exclude those values from possibly being on our graphs, because we don't want to divide by 0. So we get vertical asymptotes at 2 and -2. And do you recall, Jordan Thought Cloud, how you get the ha in this case? It's always the same, y equals 0. So when you graph these, you will put those in. Alright, so get a couple points to reinforce where this goes. So this should be y equals this function. So when you put a 0 in for x, you get 0 over -4, which is 0. And when you put a 0 in for y, you can ignore the denominator and say, when will the numerator be 0? And that's 0. So we just get the same thing. And let's get a starting point. So I take a value like 10 and I put it in here. I get 10 on the top. And 10 squared is 100 minus 4. It's 96. So I've got 10 divided by 96, which is a small positive number. So I'm going to start there. Since there's no zeros, I can't cross this axis, so I'm going to bend up. And it'll become asymptotic to this asymptote and this one. And I skip the asymptote as it was going up, and it's going to come from down. So go through the 0 and continue like that. It'll cross. It's a crossing point. And then skip down, skip across, and come from the other direction. Alright, hopefully you're getting the gist of these. We've been doing them most recently. How that will change, and I'm not going to do this one out entirely, but on this one we'll still do va-ha, xy, chart, 0, 0, 10. Still do the same thing. The only difference is that this right here works differently. It's no longer y equals 0. It's going to be the lead coefficient of the lead term, that's the term with the highest exponent in the numerator, divided by the coefficient, the number in front of the lead term in the denominator. So y equals 3 divided by 1 gives us a different way to look at the horizontals. So when you graph this one, there would be a horizontal here, up a little higher than this one. So then you would continue as we did here to find your starting point and your other points that will help you graph it. This one, we have to actually do a long division. When the degree on the top is greater than the degree on the bottom, we set up a long division problem. So some of you were fine with this and some of you were complaining. So x cubed divided by x squared is x. When I multiply, I get this. X cubed divided by x squared. This is the first step. This divided by this. So let's make this, instead of x squared, I'm going to give you one that doesn't act weird. So if you don't mind changing this example like to x minus 1. So now when I divide this by x cubed, I get x squared. X cubed divided by x this time. So I'm going to divide this expression by this. X cubed divided by x is x squared. It goes here. I multiply. I get x cubed minus x squared. Notice this does not line up with that. So we think of when you subtract, you have to subtract like terms from one another. So there's no x squared term. So think of the 0x squared. So when I change the signs and add, I get an x squared. I bring down minus 2x. Divide this by this. So in your thoughts, x squared divided by x, which is x. Multiply. This times this and this times this. Change the signs and add. We get a plus x and a minus 2x is a minus x. Bring down a plus 1. This divided by that. So we have x, a minus x divided by an x, which is just a minus 1. Multiply. Minus x plus 1, and it came out evenly, so we don't have a remainder. So on this one we have a sa. So in other words, instead of having a horizontal asymptote, it's going to be non-horizontal, often a slant. This one is actually quadratic. So this one, I made it up as I was going. I probably should have called this x squared, and it would have worked like ones you've seen. So this one's going to have some sort of strange asymptote that you're not going to find on the test. So I did review for you how this division is correct, but the actual result is going to be a quadratic asymptote, which we haven't run into, so forgive me for making up an example that you won't encounter. But once you get your slant asymptote, usually you can graph it like this, and there's some sort of va like this, and then I trained you, it's either going to be this kind of answer or this kind of answer. So you would do a sissy chart to find one point, and you'll know the rest of the graph. Alright, so we'll practice some ones in class that we can actually do. So, alright, who would have thought? Alright, so this will get you to the point where you know what is on the test and some quick discussions about each of those. So on Monday, study this so you can do well on the review sheet. It will always give you some extra credit toward your final score on your test on Tuesday. Alright, I hope you're having fun with functions. And over and out.